This video covers the review for section 5.4, part 1, testing for symmetry with respect to the polar axis, the line theta equals pi over 2, and the pole. The polar axis, when looking at polar graph paper, is what we would call the x-axis in rectangular coordinates. This is the polar axis, the horizontal axis. To test for symmetry about the polar axis, that would mean if you had some kind of graph, if a point was here, then the point would also be here. And so that amounts to taking theta and changing it to negative theta to see if the equation remains the same. To test for symmetry around or about the line theta equals pi over 2, theta equals pi over 2 is what we would call the y-axis in rectangular coordinates. And to test for symmetry for this one, if this is the point on the curve, then to be symmetrical, to have symmetry about the line theta equals pi over 2, we'd have to have that other point on the other side. Now that amounts to taking this point and looking at negative theta and then making sure that negative r is on that line. And so that amounts to changing r and theta into negative r and negative theta. To test for the pole, this is what we would call the origin in our rectangular coordinate system. If this is a point, to be symmetrical about the pole, it's going to have to be on the other side. And so this amounts to changing r to negative r. If you make those changes and the equation remains unchanged, then you're guaranteed to have symmetry about that particular one. If it changes the equation, no longer the same as the original one, then all you can say is that it may or may not have symmetry. It still can have it, but the test is inconclusive. And so for most of these problems, it really just amounts to remembering that the sine function as a graph is odd in the sense that the sine of negative theta is the same thing as negative sine theta. The cosine of theta is an even function in the sense that the cosine of negative theta is the same thing as the cosine of theta. So in testing for symmetry around or about the polar axis for r equals sine theta, we change theta to negative theta. And then with sines, the negative comes out in front of it, and it's no longer the same as what we started with. So we have to say that it may or may not have symmetry about the polar axis. For theta equals pi over 2, we change r to negative r, theta to negative theta. And in this case, because the negative comes out in front of the sine of theta, we ended up with something that is exactly what we started with. We didn't change the equation by doing this. So we can say for certain that this graph has symmetry about the line theta equals pi over 2. And then about the pole, we change r to negative r. And we have negative r equals sine theta, or r is equal to negative sine theta. So I kind of put an X through that to say, well, we've changed the equation. That one, we kept it the same. That one we change it. So I can't say that we have symmetry about the pole, but we can go ahead and say that it may or may not have symmetry about the pole. Okay, so we should recognize r equals sine theta from our previous work as a circle that sits on the line theta equals pi over 2. So you can see why it has symmetry about the line theta equals pi over 2 and doesn't have symmetry about the polar axis or the pole. Now cosine theta, we should recognize this one as the one on the polar axis. So we should expect symmetry from this one about the polar axis. So we see that because when we replace theta with negative theta, r equals cosine of negative theta, we know since cosine is the even function that it doesn't change because that negative goes away. So that remained the same. So we can say with certainty that we have symmetry about the polar axis. About the line theta equals pi over 2, we replace r with negative r, theta with negative theta. Since this theta inside goes away, that says negative r is cosine theta. That says r equals negative cosine theta, and we've just changed the equation. So we say may or may not have symmetry about the line theta equals pi over 2. And about the pole, we replace r with negative r. Solving for r again tells us r equals negative cosine theta, and we've just produced a different equation. So we now say may or may not have symmetry about the pole. And then C, r equals 4 plus 3 cosine theta. We should recognize this one from our work with graphs, that this is one of those heart-shaped graphs that look like this. Remember, the cosines always have this symmetry about the polar axis, whereas the sines have the symmetry about the line theta equals pi over 2. All right, so we replace theta with negative theta. And because the negative comes out of the cosine theta or disappears, we see that the function is still the same as what we started with. So we say that 4 plus 3 cosine theta has symmetry about the polar axis. To check for symmetry about the line theta equals pi over 2, we replace r with negative r, theta with negative theta. And as we've seen before, this negative goes away, and the negative in front of the r makes the equation turn into r equals negative 4 minus 3 cosine theta. It's changed the equation. So we may or may not have symmetry about the pole. we can see by the picture that we definitely don't have it. You need to see the graph in order to determine that. And then around the pole, or about the pole, we change r to negative r. And you multiply through by -1, and you have r equals -4 minus 3 cosine theta, which is a different equation. So again, we may or may not have this. All right, so doing the same thing for r equals 2 cosine 2 theta. The polar axis, we change theta to negative theta. And because this is the cosine, we see that this is going to stay cosine 2 theta. So we have symmetry. About the polar axis. And from our work with graphing these, we're supposed to remember that the cosine 2 theta is a 4-leafed rose. To check for symmetry around about the line theta equals pi over 2, we replace r with negative r, theta with negative theta. And in doing that, we have negative r squared. I looked at the wrong one, I'm sorry. We have negative r equals 2 cosine 2 times negative theta. The theta goes away inside, so we'll have -2 cosine 2 theta, which we've changed it. So all we can say here is that it may or may not have symmetry about the line theta equals pi over 2. We can see by the picture of the 4-leafed rose that it does have it, but with the test, you can't be conclusive on the symmetry. You have to actually look at the graph. And about the pole, to check about the pole, we change r to negative r. And so by changing r to negative r, we see that we're going to get a new equation, one that's been changed from what we originally had. So we may or may not have symmetry about the pole. All right. E and F, those were those graphs that we called lemniscates. So they look like this. Cosine was always symmetric about the polar axis. And in this case, the sine one looks like it's going to have symmetry about the pole. All right, so letter E, we replace theta with negative theta. So we have r squared equals 16 cosine of 2 times negative theta. Negatives inside cosines, they disappear. So we have r squared equals 16 cosine 2 theta. It didn't change it. So for letter E, we have symmetry. About the polar axis. To check for symmetry on the line about the line theta equals pi over 2, we change r to negative r and theta to negative theta. In this case, the negative r squared stays r squared, and the negative inside goes away because it's a cosine. So we have symmetry about the line theta equals pi over 2 now. The last one, we change r to negative r, and we're squaring that r. That becomes r squared equals 16 cosine 2 theta. That equals the original function. So we have symmetry about all three of them this time. Symmetry about the polar axis, the line theta equals pi over 2, and the pole. All right, letter F. About the polar axis for this one, we have r squared equals sine of 2 times negative theta. The negatives in the theta and the sines, they come out in front. I've lost my 16. That doesn't really change anything. So this one is changed. So we may or may not have symmetry about the polar axis. Letter F, change r to negative r. Theta to negative theta. And in this case, the r will go away from the r squared there, but the negative inside the sign comes out in front. So we produced a different equation. So again, may or it may not have symmetry about the line theta equals pi over 2. We can certainly see by the picture that it doesn't. Third one, symmetry about the pole. When you look at the graph, it certainly looks like it has it. We're going to change r to negative r, keep theta the same. Because negative r squared is r squared, we ended up with the same thing that we started with, r squared equals 16 sine 2 theta. So we can say for certain that we have symmetry about the pole. And so the beauty of this sort of thing is when you have half of the graph, you can get the other half of the graph by symmetry. So it takes some of the time away from graphing the polar equations. This is all I'm going to do for part 1. The video for part 2, we'll go over how to actually graph each polar equation. So this concludes the video for the review for section 5.4, part 1.